I welcome to this session. Now we go to discuss about one-dimensional heat equations. So these are the topic under unit number 3. So topic number 1 is classification of PDE. So then topic number 2 is one-dimensional wave equations. Now we go to the one-dimensional heat equations. So these are the three possible solutions. So already we know that one. So one dimensional. So your wave equation is so dou square y divided by dou t square is equal to a square into dou square y divided by dou x square. So already we discussed this is one dimensional wave equations. So similarly, one-dimensional heat equations also having equations. So that is nothing but so dou u divided by so dou t. So that is equal to alpha square into dou square u divided by dou x square. So in one-dimensional wave equations, so we go to find y of x comma t. So this is nothing but y of x comma t is nothing but your vibration of the particular string. X is nothing but particular distance, t is nothing but your particular time. Similarly, here also we go to find u of x comma t. So this u is nothing but temperature, heat temperature in the rod or sheet. So anywhere. So is x is nothing but particular distance, t is nothing but particular time. In the particular distance, in the particular time, what is the temperature in the particular rod or particular sheet we go to discuss now. So now we will solve this one-dimensional heat equations. We will get a three possible solutions. These are the three possible solutions. The first solution is u of x comma t is equal to a into e power lambda x plus b e power minus lambda x c into e power a square lambda square t. Similarly, for the second solution, so u of x comma t is equal to a cos lambda x plus b sin lambda x into c into e power minus a square lambda square t. Then the final solution, third solution is y of x comma t is equal to ax plus b into c. So these are the three possible solutions. So anyway, we having the based on the constant k. So k may be a positive, k may be negative, or k is equal to 0. So under these three conditions, we got these three solutions. So we want to choose which solution is the suitable solution for solving one-dimensional heat equation. So equation 2 is the most proper solution. In the possible solution, we go to take the 3 as the proper solution for solving one-dimensional heat equations. So these are the boundary and the initial conditions. So the type number 1, case is 1, that is nothing but the temperature at the ends of the rod kept at 0. So therefore, let us consider any rod. So one end we have taken as A, so another end taken as B. So here in that particular point A, theta 1 is the temperature and theta 2 is the temperature for the point B. So initially, so both the ends are 0 degree Celsius. Both the ends are 0 degree Celsius means, so this comes under type number 1. So that's the given here. The temperature at the ends of the rod kept at 0 temperature. So both the ends are 0 means comes under type number 1. So here x is nothing but 0. Suppose if it is the length of the rod is L, so x is nothing but L. So when x is equal to 0, your boundary condition, the temperature is 0. Similarly, for when x is equal to L, another end, when x is equal to L, another end is also the temperature is 0. Both the boundaries are 0 temperature. That's they are telling. Okay. So what is t greater than or equal to 0 means for any t. So after some time t may be increasing, 1 second or 2 seconds or 5 seconds or 10 hours, 20 hours. That t is a time for here. At any time, after any time, so always the particular both of the places will be 0. So that's the boundary condition for the boundaries. The next one is the initial conditions. So before starting time, that is taking the count of time. What is the condition now. Initially, what is the condition of the rod? So that is given u of x comma 0 is equal to f of x. This amount of initial temperature is there. So this will be lies between 0 and L. That x is nothing but lies between 0 and L. So that f of x may be trigonometric form or algebraic form. So this is the boundary and initial conditions for one-dimensional heat equation for the both the ends are ends of the rod are kept at 0 temperature. Okay. So now we go to see the next slide. Now we go to tell the f of x is a trigonometric form. The first form, the uniform rod of length L. So let us consider any rod. So that rod length is L. So therefore here x is equal to 0 at the point A and x is equal to L at the point B. So which heat flows is insulated at the sides. So the ends are kept at 0 temperature. Therefore here also 0 degree Celsius and the another end also 0 degree Celsius. The initial temperature of the interior points of the bar is given by K into sine cube pi x by L. So therefore that x lies between 0 to L. Therefore in this rod the initial temperature is so K into sine cube pi x divided by L. So that is nothing but our f of x. Okay. So find the temperature distribution in the bar at any time t. So therefore we need to find what is our u of x comma t at any time t we want to find. So we know that one dimensional heat equation is dou u by dou t, that is equal to alpha square into dou square u by dou x square. So therefore you can solve this, we get a 3 solution. In the 3 solution, so this is the proper solution. So what are the boundary conditions? U of x comma 0 comma t is equal to 0 for all t greater than or equal to 0, first condition. Second condition is u of L comma t is equal to 0 for all t greater than or equal to 0. So the third condition u of x comma 0 is equal to k into sine cube by x by L. So x lies between 0 and L. Here your a, lambda and b are constant terms. We want to determine that cases. Okay. So therefore here this is the equation number 1. So this is a possible in that possible solution, this is the proper solution for the one dimensional wave equation. So that is nothing but u of x comma t is equal to a cos lambda x plus b sin lambda x into c into e power minus alpha square lambda square t. So now I go to apply that condition number 1 in this equation number 1. So therefore, so I go to replace. We want to apply the condition number means instead of x we go to replace 0. Therefore here instead of x I go to replace 0. Wherever x is there we go to replace 0. Therefore cos lambda x instead of this x I go to replace 0. Instead of sin lambda x I go to replace 0. So if you are replace means we will get this part. Okay. So now we know that one. So u of x comma 0. So our u of x comma 0 is nothing but 0. We got to replace it here. So u of x comma 0 is equal to 0. So cos 0 is 1. Sin 0 is 0. So this keep as it is. So b into 0 is 0. So therefore simply we have a plus 0 is a. Therefore this is a. So c into e power minus alpha square lambda square t. Now, so these two terms, let us consider term number 1, term number 2, that is T1, T2. The term 1 is our product, term 1, term 2 are product cases. So term 1 into term 2 is equal to 0 means either term 1 is 0 or term 2 is 0 or both are 0. So these are the 3 possibility. So suppose if it is the term 2 is 0. So let us consider, suppose if it is term 2 is 0. So that means, so this is instead of not equal, suppose if it is equal to 0. If you are consider this is 0, our solution always tends to 0. Why? Because, so this is our solution of the one dimensional heat equation. Suppose this is 0. So 0 into whole thing, 0 into anything is 0. Therefore, our u of x comma t is always 0. So that is not possible. Why? Because already the temperature is 0. Why? Because already we consider some non-zero temperature is there. Therefore, if we are consider this is 0, the solution is always 0. Therefore, our assumption is wrong. Okay, this assumption is wrong. So therefore, we know that one. So this is only the possible c into e power minus alpha square lambda square t is not equal to 0. Therefore, we conclude that a is 0. Suppose the same case we go to apply in the previous slide. Suppose if it is a is 0, surely we know that one, this one only tends to 0. The solution is non-zero. Therefore, now our assumption a is 0 is a correct one. So therefore, we will get a is 0. Now I go to replace a is 0 in the previous solution. So here instead of a, I go to replace 0. The whole term tends to 0. So we will get the updated solution is, this is our updated solution. So b into sine lambda x, c into e power minus alpha square lambda square t. So first condition is over. So now I go to apply the second condition. What is our second condition? So our second condition is u of l comma t is equal to 0. So instead of x, I go to replace lambda. Sorry, instead of x, I go to replace l. So here l comma t is there. So here, so instead of x, I go to replace l. So u of l comma t. So instead of x, I go to replace l. So therefore, already we know that when u of l comma t is 0, therefore only this possibility. So here also either b is 0 or sine lambda l is 0 or e power minus alpha square lambda square t is 0. So these are the three possibilities. Already we discussed this is non-zero. Okay. So suppose if it is b is 0 means again the whole term tends to 0. The solution is 0. Therefore we conclude that b is not equal to 0. Only possibility sine lambda l is equal to 0. Okay, suppose sine lambda l is 0 means here the solution not affected here. So therefore we conclude that sine lambda l is 0. So therefore here we discuss sine lambda l is 0. I bring the sine another side, we'll get sine inverse of 0. Sine inverse of 0 is nothing but n phi. So bring this, we need to find lambda. Bring this l another side, we will get, so lambda is equal to n pi by l. Now we can replace lambda is equal to n pi by l. So in this updated solution too. So here and here. So instead of lambda, we go to replace n pi by l. So we'll get the updated solution is this. So where n runs from 1, 2, 3 up to infinity. Okay. So now n runs from 1 to 3 up to infinity. So b and c are constant terms. So b, c is constant terms. So again, multiple of two constant term is again another constant term we have taken as bn. Okay. So therefore now we go to replace all those things. I go to write the most general solution. The most general solution is like summation n is equal to 1 to infinity bn into sine n pi x by l into e power minus alpha square n square pi square by l square into t. So here n runs from 1 to infinity. Therefore, so each term in n is equal to 1, n is equal to 2, n is equal to 3, we go to replace it and add it. So you go to add the temperatures. So that is the reason I go to use summation for here. So summation n runs from 1 to infinity. So that is the temperature of this. This is the most general solution. So in that most general solution, constant is there bn. So we need to find this. What is our bn? Now I go to apply condition number 3 in equation number 4. So here what is our condition number t? U of x comma t is equal to, instead of t I go to replace 0. Therefore wherever t is there only, t is here only. Instead of t I go to replace 0. So 0 into the whole thing tends to 0. Therefore this is e power 0. So e power 0 is nothing but 1, or u of x comma 0 is nothing but f of x. That is the fourth conditions. Now we go to replace f of x here. So instead of our f of x is k into sine cube by x by l. So we know that one. So sine cube theta is nothing but 1 divided by 4 into sine, um, 3 sine theta minus sine 3 theta. So this is the formula. So here I replace sine cube theta is nothing but 1 by 4 3 sine theta minus sine 3 theta. So therefore instead of this I go to replace k. So already k is there. So k into 1 by 4 is k by 4. So 3 instead of theta we go to replace this pi x by l. So therefore 3 sine pi x by l minus sine. So already 3 is here, therefore 3 pi x by l. So that is equal to summation of this. Now I go to replace n is equal to 1 here. So in this part, if I replace n is equal to 1, we will get this case. So n is equal to 2, we will get n2 into, so instead of n, here and here I go to replace the value. Okay. So therefore, instead of n, I go to replace 2, we will get b2 into sine 2 pi x by L. Similarly, instead of n, I go to replace 3, instead of n, I go to replace 4, 5, 6, and so on. So now I go to equating the coefficients on the both the side. So here I go to consider sine pi x by L. I go to equating the both the sides. So in your left hand side, so coefficient of sine pi x by L is nothing but 3k by 4. In your right hand side, sine pi x by L is nothing but coefficient is b1. Similarly, so next sine cube pi x by L. So sine 3 pi x by L, go to equating the coefficient of sine 3 pi x by L. I go to equating this. So here it is coefficient is nothing but b3 in my left hand side. So coefficient of sine 3 pi x by L is minus k by 4. Therefore, b3 is nothing but minus k by 4. So what about the remaining terms b2, b4? There is no sine 2 pi x by L. The means for that I go to replace. So 0 times of sine 2 pi x by L plus. So 0 into anything is 0. Therefore, the meaning is never changed. Therefore, coefficient of sine 2 pi x by L is 0. Therefore, here the coefficient of sine 2 pi L is b2. b2 is 0. Similarly, we can find the b4, b5. Remaining terms are 0. So in that most general solution, so we go to replace Bn. So only B1 and B3 are non-zero. B1 and B3 are non-zero. Remaining B's are 0. So therefore, in that most general solution, here I go to replace n is equal to 1. So that is non-zero. So B1 is non-zero. N is equal to 2. So therefore, B2 is 0. N is equal to 3. So B3 is non-zero. N is equal to 4. So B4, B5 remaining term tends to 0. If I replace any B value, B is equal to 4, 6, 7, 8, that 0 into sine term exponential terms to 0. Only if you replaced 1 and 3, then only we having the value. So if you replace n is equal to 1 and n is equal to 1 and 3. So we'll get, so b1 into sine pi x by L into exponential term plus b3 into sine 3 pi x by L into exponential term. Therefore, now I go to replace instead of b1, we go to replace 3k by 4 instead of b3. So we will replace it minus k by 4. Therefore, we will get a temperature distribution of the particular distance in the particular time. So now we go to see the next problem. So now it is in the case of algebraic form. The heat flows through a uniform bar of length L, so which has its sides insulated and the temperature at both the ends are kept at zero temperature. Since if the ends are 0 degree temperature, therefore it comes under type number 1. If the initial temperature at the interior point of the bar is given by k times of Lx minus x square, so the length of the bar is L. Therefore, x lies between 0 and 1. So as usual, what we discussed in the previous problem, the same thing. This is a one-dimensional wave equation. So this is the boundary conditions, two boundary conditions, and one initial conditions. So this is the proper solution for the one-dimensional heat equations. So now I go to apply condition number 1, equation number 1. Instead of x, I go to replace 0. So then we will get a is equal to 0. So replace a is equal to 0 in your possible solution. So we'll get this term tends to 0. We will have, so this is the updated solution. So take it as equation number 2. Now apply condition number 2 in equation number 2. So instead of x, we go to replace L. So we will get, so lambda is equal to n pi by L. So replace lambda is equal to n pi by L in the previous solution. So we will get this case. So n tends from 1 to infinity. We will get the most general solution. So now we go to apply the condition number 3. So in that condition number 3, we will get u of x comma 0 is equal to summation n is equal to 1 to infinity here. U of x comma 0 is nothing but f of x. So that is our f of x is nothing but bn. So here we go to find bn. So therefore, instead of f of x, we go to replace given f of x. So this is nothing but Fourier half-range sine series formula. In that Fourier half-range sine series formula, we need to find Bn. So Bn is nothing but this. So therefore, this is your u v dx. So using the Bernoulli's formula, where Bernoulli's formula is u v dx is nothing but so u v1 minus u dash v2 plus u double dash v3 minus up to etc. So here these are u v. U is u dash, u double dash, u triple dash is nothing but differentiation. V1, V2, V3 is nothing but integration. So integration of v is nothing but v1. Similarly, integration of v1 is nothing but v2 and so on. So after we found v1, v2, v3, u1, u2, u3, so replace it here, we will get this point. So now I go to apply the upper and lower limits. So conclude it will get Bn. So after found your B1, you can replace in your most general solution here. Replace your most general solution, will get the solution is this. So this is the problem for practice for you to practice it and check whether you have got this.